The purpose of this video is to present some highlights of the LMS work in the robotics field. LMS is active on research of advanced tools for the design and control of highly flexible production systems and on engineering research of industrial automation and robotics applications, advancing the state-of-the-art in cutting-edge manufacturing technologies. The introduction of dual-arm robots in human-based assembly lines will eventually increase the automation level, enabling the human to work on value-added tasks. In this direction, the adoption of dual-arm robots seems promising, as it allows for multitasking, as well as space and cost efficiency, by eliminating the fixtures and gripping devices. The dual gripper concept has been integrated into the Comau industrial dual-arm robot, allowing the handling of big and heavy parts along with the smaller ones, without requiring the changing of tools. In this case, with cooperation with the Fiat Group, LMS designed the automated assembly sequence, involving both humans and robots working together. Similar to the human operator that uses both arms, the dual-arm robot was able to handle a 12 kg vehicle traverse, using coordinated motions of both arms, without complex gripping devices. Without changing grippers, the robot using both arms was able to assemble in the traverse slot the fuse box that weighed around 0.5 kg. Using a traditional push-and-start screwdriver, which can also be used by a human, the dual-arm robot was able to fasten screws on the fuse box, with the same grippers. Another task involved a wire harness placement on the top of the traverse, since the cable is a flexible part, requiring the human capabilities of problem-solving and complex parts handling. This part is assembled by a human. In order for humans and robots to have a close coexistence, advanced and certified safety solutions are required. In cooperation with PILS and Comau, LMS has integrated the safety eye sensor, ensuring that both humans and robots will be safe in the same workspace. The Human-Robot Station Controller allows the execution of both human and robot tasks in a safe way. A high-level task description has been programmed in order to be easily monitored by a non-expert user. The user is able to signal the start and the end of a human task via gestures, voice commands or buttons on the user-friendly graphical interfaces. The communication framework was based on ROS middleware. Safety is ensured by the different safety zone configuration. Intuitive human-machine interfaces have been developed for reduction in the programming time. In this direction, the user is able to move the robot by using external software tools, such as motion planning libraries. The user selects the target position in a simulation environment and a path is generated. The path is tested in this environment and is further sent to the robot for execution. LMS has also worked on the development of applications for dual-arm concurrent motion planning. A multi-criteria decision-making framework was used in order to allow the generation of dual-arm motion paths. In the configuration space, the paths were validated both in a simulation mode and on a real dual-arm robot. The human can easily move the dual-arm robot with simple gestures. The cooperation of both arms is possible in this mode as well. The robot's speed is adjusted at a low level, following the same logic as that of the traditional programming approaches. Similar to the body gestures, the robot is commanded by the human via hand gestures. The robot follows a path along a user frame, according to the human commands. The use of an alternative offline programming approach was proposed, enabling the dual-arm robot to mimic human motions. The human data were captured in a virtual reality environment, and were further processed and executed by the robot. In this way, the programming time is significantly reduced, while accuracy issues still need to be improved. The simulation of flexible parts, such as the wire harness, was also investigated, through the evaluation of different simulation platforms and physics engine machines. LMS has developed its own physics engine along with testing the existing ones. The latest research trends envisage the interaction with human operators with industrial robots. However, an industrial environment with large, high-powered robots, without safety fences, can be a dangerous place for an operator. Although safety technologies are being developed and tested, a key point to their success is the achievement of operators' acceptance. To this direction, LMS focuses on providing efficient means of supporting the humans under a safe collaboration scheme. Current industrial practice demands that people perform many assembly tasks on their own. This leads to fatigue accumulation, quality defects, due to a lot of repetitive tasks and a lot of training for the operators. On the other hand, the operators possess great capabilities when it comes to their dealing with unexpected occurrences, or performing dexterous tasks. Robots can deal with repetitive operations without compromising their performance, as they can manipulate heavy parts more easily and they are more accurate in performing their tasks. Unfortunately, the current safety policies demand that humans and robots be separated by industrial fences, prohibiting their direct collaboration. Our work at LMS is to create strategies in order for fences to be removed and human operators and industrial robots to have a closer collaboration in a safe way. In collaboration with the industrial partners of Electrolux, Comau and Pills, a white goods pilot case concerning the refrigerator assembly has been set up. Against the current practice, the taping operation has been replaced with the robotics sealant application. Workspace and task sharing between humans and robots has been enabled, while the tools in support of the human-robot collaboration are integrated during execution. Such tools involve power and force limiting software as well as tactile and capacitive sensors, respectively. An automotive pilot case for the rear axle assembly has been set up at our premises, with the support of Tofas Fiat Group, Comau, CRF and Pills. A human-robot collaborative task planning module, based on artificial intelligence techniques, has been developed. Such a tool automatically generates the 3D layout of the cell, as well as efficiently allocates the tasks for the efficient exploitation of both human and robot capabilities. In order for the human operator's safety feeling to be increased, a human operator support application, based on augmented reality technology, has been developed. Such an application is integrated into the execution system, in order to provide the required information online. The operator is provided with visual and audio alerts, visualization of the safe working volumes is performed, assembly instructions are introduced to the user. Through the visualization of 3D models, production information is also provided upon user's request. This application interfaces with a smartwatch enabling device, in order to receive the operator's input. Demonstration of the software for the management and synchronized handling of a robot with a gripper in cooperation with a welding robot using the AutoRaycon control software. An autonomous communication among the resources without external PLC for synchronization. All robot instructions, assignments and precedence constraints were stored into an ontology repository, while the user had the ability to monitor the process through a dedicated GUI. The communication between the part, on machine-to-machine protocols, is based on the ROS framework. Every resource has its own ROS interface. Enhanced robustness of the system is possible, because there is no master-slave relation among the components of the line. The ROS framework is used for the communication among all the entities, robots, grippers, vision system and ontology. Rescheduling takes place. Due to an unexpected event, the mobile robot has to move to another station and take over the workload of the handling robot. In order for that to be done, the gripper of the other robot has to be attached. The vision system's role, in this scenario for the consumer goods industry pilot case, is the detection of the shavers, in the specified field of view in the conveyor belt, as well as the features measurements, in order for the real-world coordinates, in a known reference frame to be found. The robots should be able to grasp the parts, which have a complicated 3D geometry, while they are moving onto a conveyor. Smart 6 robots pick up the randomly positioned and oriented handles from the feeding conveyor and position them onto the track conveyor. The 3D vision system recognizes the initial position of the blades and compares it with the target position that the user has defined through the USmart-friendly programming interfaces, which will be demonstrated at the freestyle round. In the next step, the robot gripper picks up the pin and heats it, By using an automated torch that is installed in the cell, the robot directs the pin to the insertion position against the real part, via the high-accuracy vision system. During the pin insertion, advanced force sensing and control algorithms are used in order to regulate the insertion depth, and ensure that the surface or the ceramic core should not be damaged. The robot that is equipped with a screwdriver moves on to pick the first screw on the right side. The screwdriver includes a magnetic tip that can pick the screws. Based on the CAD information extracted during the programming phase, the robot moves on to the correct hole, compensating for any errors through the vision system. During the screw insertion, force sensing is applied in order for the proper alignment to be ensured, while the applied torque is ensured by the screwdriver controller.